Good evening. Shortly, we will hear an interesting lecture by Dr. Yaakov Amitai on start with pilot helmet and finish with Ray-Ban glasses, a breakthrough technology which enabled the use of compact and economical display sources while maintaining excellent image quality with no distortions or artifacts, with an extra wide field of view, and consequently allows for the first time the design of a smart glasses that can be adopted by the mass market. This is part of a webinar series organized by Photonics Israel on various aspects of photonics. The photonics industry is a technological and economic growth engine in the world. In Israel, it contributes about $6 billion annually to the Israel economy. Photonics Israel operates within the Engineer Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with photonics entities in the world. My name is Shlomo Glaser. I am the manager of Photonics Israel. Dr. Yaakov Amitai is the pioneer of substrate-guided elements for the near-eye display field. He was the head of optics group in ELOP and founder of and CTO of Lumos, where he invented its reflective substrate-guided elements. Dr. Amitai has 75 granted patents in the US, and he is the founder and CTO of the Oorym. Q&A will be at the end of the lecture, so please post your questions on the chat tab. Dr. Amitai, the stage is yours.
Thank you very much. Okay, I share the screen. Okay, can you see it? Shlomo?
Yes, we see you perfectly.
Okay, so I'll start. Okay, good evening to all of you, or good morning, depends where you are. My name is Yaakov Amitai from Oorym, and as Shlomo said, I'm going to take about how to go from a pilot's helmet to a pilot's Ray-Ban. And I also try to answer the question, is it can be to have it all? So let's start. What I'm going to talk today, first of all, instead of introduction, I'm going to give you a brief history lesson. Actually, it's my personal history, which connected to the near-eye display using substrate-guided element. And now, after that, I'm going to discuss briefly about the differences between conventional optics and diffractive optics, and how they are usable for a substrate-guided optical element. Then I'm going to state a few well-known axioms, and I'm going to ask, are they still persistent? Then eventually I'm going to talk about our technology, the SPS, and at the end of the talk, I'm going to tell you what the meaning of SPS. And instead of summarize the talk, I'll tell you a brief story. So, the near-eye display is quite an old story. If you go back to year 1916, this is the first patent which is applied and granted for a helmet-mounted display. And if we go 100 years ahead, we see that it has not been changed so much. You see that this helmet, this is a visor display of Thales, and the optical element that you see here was produced by Lumos. But you see that the entire system is quite similar to the 100 years old. And we can ask, has something has changed during the last century? And the answer is certainly yes. You see that here we have a bayonet, and here you don't have. So, before we start talking about the display system, I must emphasize that there are three main criteria for near-to-eye display: image quality, and image quality. Which means, before you start talking about the other parameter, first of all, you have to get good image quality. If you don't have it, Don't even start to talk about the other parameter. This should be must. And when I say image quality, I don't say that you are going to test it and to show it by flying dragons, because the flying dragons have some tendency to kill all the artifacts, so you cannot see it. It's a very good, it can have very good impression, but if you have any flu, you will not see it. So this is not a good, this is not let's say, a good example. A much better example, for instance, if you see a resolution chart. With a resolution chart, you can see the brightness, you can see the contrast, you see if the white is white and the black is black. So if someone show you, let's say, a near-to-eye display and show that it's full of dragon, say, I don't want to see dragon, I want to see resolution chart. So let's start the history lesson. I start work on a substrate-guided element 32 years ago when I postdoc in the laboratory of Professor Joe Goodman in Stanford. He worked then on optical interconnect, and when I start working with him and I suggested some solution, he told me that it could be wonderful if we can take the entire optical system and contract it inside a single substrate. So I asked him, so how the light wave will propagate from the various nodes of the system? And say, oh, simple, by total internal reflection from the external surfaces of this substrate. So then I started to work, and my first work there was for optical interconnects. As you see here, the system was very simple. We have hologram in and hologram out. The light was collimated and coupled into the substrate by the first element, first hologram, and was coupled out by the second hologram. You see, quite a simple system, isn't it? Not so much. Why? Because we have to record and reconstruct this system with different recording and reconstruct conditions. We record it in green light and reconstruct it for the near IR. And the result is that if we record it with spherical wave, we get enormous aberration. You see that the spot size here is more than 1 millimeter. So we have to record it with a corrected light waves. And as you see here, we have diffraction limit. Here you see the iris, the Bessel function of the image. And this was our first work. It was published exactly 30 years ago in Applied Optics. But again, it was just a modest starting, just 1 point to 1 point. After Stanford, I returned to Israel. I've been in the Weizmann Institute, and we expanded our work for a wider field of view, not just a single point, but a whole image, which is get out from the display source. It is collimated and it's trapped inside the substrate by total internal reflection. Again, we have coupling in element here. We have coupling out element there. The light are propagated in between by total internal reflection and then coupled into the eye. Certainly, it is much more complicated than the system we saw before. But eventually, we succeeded in getting let's say, reasonable image. We wrote our first patent in 1993 after 2 years of working. And 2 years later, we published more detailed paper about it. Then we have some twist in the story. Because one day I got a message that a very important person is going to visit the Weizmann Institute, and they want me to host him and to show him the helmet mount, let's say the near eye display, which is based on substrate-guided element. And I told him, are you crazy? It's not ready yet. It's just a demonstration. And I cannot show this to this very important person. So they told me, okay, you have another 2 weeks to prepare it. It's a lot of time. You will be prepared. So I have no choice. I worked a lot. And fortunately, it was ready just 10 minutes before this very important person came to my laboratory. The reason why it was so fortunate, because it was a very, very important person. It was the late Prime Minister Yitzhak Rabin. I came into a lab, I saw in the demonstration. What I tell you is very smart guy. Don't forget, he was not only the prime minister, he was also the chief of staff. So he know everything about military equipment. He asked the right question and understand anything that I explained to him. But look what he said when he just have the first glance on the demonstration. Say, oh, it's a helmet mounted display. It's beautiful. It's colorful. So just remind this word colorful. He was not the only visitor at my lab in this day. There was another very important person, the president of the Weizmann Institute, Professor Chaim Harari. And after I finished the demonstration, he told the prime minister, you know, Mr. Prime Minister, this demonstration, it is very simple, and yet it can have a tremendous impact on the display field. So Professor Harari is a very smart guy, but let's look about this statement. The technology of substrate-guided element, which I demonstrated there, certainly has many advantages. First of all, it can be very compact. It can be low. The white it can have a very low white. And it has the potential to have something which is similar to a conventional eyeglasses and still project image into the viewer eye. But it is simple. Spoiler, it is not simple. So I continue to work. I just later on I moved to Op, and I continue my research on this subject. And the next step was to develop a two-dimensional expansion. And as you see, we have now 3 holograms, one coupling in, one expand in one direction, and the coupling out expand in the second direction. So we can have a very small coupling aperture, very large output aperture, but it's not simple. White is not simple. By the way, this is the patent that we wrote in the year 1998, but it is not simple. To show white is not simple, let's go to the Maxwell equations and start with the simplest optical, let's say, a law, the first law, and with the reflective optics. You will see the reflective optics, the direction of the output beam is determined only by the shape of the system. Alpha in is equal to alpha out. If you go to refractive optics, a little bit more complicated. It also depends on the shape of the optical element, but it also depends on the refractive indices of the materials. And if you go further away to diffractive optics, we see that here the dependency on the shape of the element is less important. It depends mainly on the grating function of the grating. So let's say we used to separate between the refractive and reflective. We call it conventional optic, and diffractive is non-conventional. It doesn't matter. Now, remember this equation, because this equation, we should stick with it for the next transparency. It causes us a lot of troubles. So there are 2 physical problems for diffractive optics, real physical. And they are, let's say, a result of this, let's say, peculiar equation. You see that the output depends on the input, but it's a sign equation. It's sort of not a linear equation. And what is the outcome? The outcome is that we have problems for the, let's say, for a monochromatic image, and also for the field of view of the multicolor image. These problems arise from the mere facts that when we use substrate-guided element, the field of view inside the substrate is usually limited between 40 degrees and 70 degrees. We'll see in a minute why. So let's start with the monochromatic image. You see, this is the equation that we discussed before. And we can see as a result of this equation, if we want to see what is the actual difference, not between the sign but between the angles themselves, we can get these results outside of the, let's say, this is the first order of a Taylor expansion. And we have here very ugly term, which is a cosine. Here, the cosine is our enemy because it reduces the actual field of view. So you see, this is why we have problem. If the angle is below 40 degrees, then we are below the critical angle. The light cannot be trapped inside the substrate with total internal reflection. If it's above 70 degrees or so, then you see that the light ray is leaping over the output aperture. We cannot use it. So this is the reason for the limit. And because of this limit, we have this equation. So we see that the field inside, the ratio between the field inside and the field outside is decreased by a factor of 2, which means that if the field of view inside the glass is 30 degrees, then outside of the glass, it will be something like 16 degrees. This is inside the substrate. When we get out of the substrate, we get that the field of view is around 12 degrees. It's better than, 24 degrees, it's better than 16, but still we have some construction in the field of view, and we are very limited. We'll discuss it a little bit more. But here our troubles, we have a lot of trouble yet, because if we go to multicolor image, and now we develop this equation for the difference between two rays that have the same incident angle, but have different wavelength, we see that the difference between the angles of these two wavelengths depend, of course, on the difference between the wavelength and again, by this enemy, the cosine of the cosine angle of the propagating wave. Here you can see that white ray that impinge on the input hologram is diffracted at completely two different angles. So let's assume that this color is blue, green, green and red, which is 450, 550, and 650. We see that the output angle of the blue is too low for the total internal reflection, and for the red is too high, which means we cannot even use a single ray, white ray, to transfer for imaging in this single substrate. The bottom line that we cannot use single substrate for color imaging. So see, we can have some solution. What is the solution? To take 3 adjacent substrate, each for each color, R, G, and B, combine them together, and get colorful image. Simple, isn't it? Not simple at all. You'll see in a minute why. By the way, I published this idea. I think this is the first time that this idea of using 3 different subsets was published in this patent. But however, I didn't claim a special patent for it because I thought that it's obvious. It have no new, let's say, no inventive steps. So I didn't claim for a patent for this idea. But it was stated. It was stated in this patent. So it is not simple at all. Why it is not simple? By the way, I'm going to repeat the word simple will be appear repeatedly in my talk. So why it is not simple? You see, this is the coupling out element. As you see, this is coupling out element. We want it that the output image will be uniform. So, but you see that the light, the first ray get out here, and the second here, and the third here. And if you get just a constant efficiency here, then the light will not be efficient because the brightness will be dropped down. How we can compensate it? We compensate it by using a coupling out element having let's say non-uniform reflectance, which means that the reflection, or let's say the diffractive efficiency, increase as a function of the propagation direction. Of course, this we cannot do it by step because each direction have different steps. So we just get, let's say, something close to linear change in the efficiency of the hologram. Now, let's see what's happened. We start to propagate, so it increased, we got an increase, but this is for the rays who propagate the first time. Now, after this ray start to coupling out at the second time, we see that it will drop, excuse me, we see that the efficiency will drop down because this is the second reflectance. It will increase again, and again, it will drop down, and this will be the shape of the coupling out. It is not a disaster if it's just a single wavelength. But however, we have RGB, we want to image a full color. And again, remember this equation. So what we want, because we want a white image, this is what we want that will be the output of the beam. Unfortunately, since various color propagate inside this substrate in a different direction, this will be the output, which will mean that we get a smeared image. It will not be white, it will be let's say a dirty white image. So what we can do, there are two things that we can do. First of all is to use laser light, pure monochromatic light for this free substrate, and again, to use a very accurate registration between the three gratings. Not simple at all. So you can ask how Prime Minister Rabin say, oh, it's colorful, it's beautiful. Where's the color? Even now we cannot do it with single element. How I show Prime Minister Rabin a colorful image 27 years ago? So there is, the answer is that what Prime Minister Rabin saw, which means at the right side it was blue, at the left it was red, at the center green. We illuminated with a white light. For demonstration it was good enough. Naturally, we cannot use it for let's say for real practical system. Okay, let's go into reflective optics. Reflective optics have some advantage over the diffractive. First of all, the efficiency, unlike the diffractive, which is very complicated to control the efficiency, in the reflection is quite simple. You control it by thin film coating, which is, let's say, the well mature technology. But more important, the reflection equation, remember, this is first no alpha out equal to alpha in, which means we have no dispersion at all. Which means if we have color image, all the colors are reflected at the same angle. So we can reconstruct the image and have a full color image even with a single substrate. Is it simple? No, it's still not simple because there are other troubles. As I said before, there are advantages for the reflective, but there are also disadvantages. One of the disadvantages is that the light rays are bending according to the shape of the element. We cannot put, like in diffractive substrate, to put the element here. It should be positioned at an oblique angle in order to couple the light out, as we couple the light in. And this let's angle impose a limitation, and let's say this relation between the thickness of the substrate and the size of the aperture. And the outcome is that we can either have a thick element, and it will be very bulky and system, if you want to get a wide field of view, and if you want a thin element, like in the eyeglass, then the field of view will be very small. So it's not simple. Is there a solution? Yes, we can try a solution of using multifaceted structure. Here, instead of a single coupling out facet, we have a lot of facets, 2, 3, 8, 10. Then naturally, we can increase by a factor of n the output aperture. This idea was published 30 years ago by Migozi from Thomson CSF, and it looked very simple. Is it simple? Not yet, it's not simple. Because as you can see, the light incident on the coupling out element, because it's, let's say, it's oriented at an angle, it's not coplanar with the major surface, the light rate impinge on this surface with two different directions, from this direction and also from this direction. Here, the second reflection is our enemy. We have also already two enemies. One enemy is the cosine in the diffractive optics, and one is the second reflection for reflective optics. So let's see what happened. For the first ray, everything is okay. The first ray got going out here. The second reflection is from here. If the reflectance here is higher than here, then everything is okay. But let's see what going with the second ray. This is the first reflection, but between the first and the second, we see that the ray impinge here in the second second incident angle on this reflecting surface. lo and behold, it is reflected in the wrong direction, and these two rays disappear from the image. The net outcome is that instead of white image, we get a strips image with black strips. So eventually, Thomson CSF aborted the patent because it didn't work. Okay, next step, year 2000, I left LOP, and before I joined Lumos, I had an idea how to solve the problem that I just described before. This is the patent that we published in the year 2000, the first patent of the LOE. So how we solve it? We noticed that the two different rays, the two incident rays, that is completely two direction. You see, for the low angular region, we want partial reflection, that the light will couple up into the user eye. For the high angular region, we desire no reflection. So the actual curve that we required for the coupling out element is this curve. It's quite, let's say, a peculiar one, because you see that at the low incident angle, the reflection should be 0. And for the low angle, it should be a partial reflection, but it works. You see, the system of Thales that you saw before works for some years very, very successfully with this idea. But still we have, it is not simple. As you can see, now this second ray, the red ray, we see that we solve the problem because here the reflectance is 0. It's not really 0. We have some residual reflectance of a few percent, but let's assume that is 0. So you see here, it is reflected the first time. Let's assume the reflectance here is 30%. Okay, so this 30. But here, this ray lost 30% here, and only then it reflects here. So the reflectance here, let's say the efficiency here, will be much lower than here. And the net outcome will be, instead of having black strip, we have gray strip. It is a problem. It's not simple. Eventually, this problem can be solved, but you better ask the people from Lumos how this problem can be solved. So okay, now I'm going to talk about these following 6 axioms in details. I just want to say something. I'm going to compare now the technology of Oorym, the existing technology of the diffractive or the reflective of Lumos. There are some other companies that use reflective technology. I want to emphasize these two technologies are excellent. They are wonderful technologies, and you can make wonderful systems with them. But I let the people from this company to talk about their technology. I'm going to, let's say, to emphasize the advantages of Oorym's technology. So let's start it with these 6 axioms. The first axiom said that you cannot achieve a wide field of view with a simple system. Why? The reason is that because you have, if you want wide field of view, you have to increase the output aperture, which means with the LOE, you have to increase the number of partial reflecting element, and with the diffractive element, you have to increase the aperture of the output hologram. In both cases, make the system quite complicated. The second axiom is you cannot have good image quality and still keep the low fabrication cost. And yeah, we must emphasize that in order to achieve good image quality, let's say the image should be uniform and flawless over the entire aperture and over the entire field of view. So let's see what's going on with the LOE. The LOE, we have, let's say, if we have wide field of view, we have a lot of surfaces. You see that all the surfaces should have the same, let's say, not the same efficiency, different efficiencies, but the same output. They should have the same color. They have the same white. It's not simple. And similar thing go with the diffractive element, because this is, let's say, complicated coupling out element, because the efficiencies should be changed linearly, and it's very wide. So it's quite complicated to manufacture such a system. Bottom line, good image quality, you have complicated and not so low cost system. Okay, now go talking about plastic. Plastic is very popular, tend to be very popular in optical system. Why? Because it has a low weight, in factor of 2 or 3 compared to glass, and of course in a sense of eye safety. Not because of cost. You have to know glass is cheap, but these 2 parameters are important enough. So why not using plastic for these 2 systems, the reflective and the diffractive? And the main reason is that unfortunately, these 2 elements, coupling out element for the diffractive and the reflective, are polarization sensitive. And we know that plastic usually have birefringence effect. So you cannot use polarized light with elements that have a birefringence effect. Okay, so let's go to the other axiom. The other axiom is that the external field of view is bounded by the internal field of view and the term of the refractive index. So let's look, for instance, on the reflective element. Let's assume that usually the refractive index is bounded 1.7, something like this, and the internal field of view is something like 22, 25 degrees, and then the outcome is that the total field of view is something like 36, maybe you can stretch it to 40 degrees. However, let's look what happened in the diffractive element. Here, the problem is more severe because you see this, remember this enemy, this cosine? Because of this cosine, the field of view is even smaller. Even if we use a larger, quite a higher refractive index of 1.8, and let's assume that the field of view inside the glass is 30 degrees, then the output, let's say the external field of view is bounded by 28 degrees. As far as I know, this is the maximum achievable field of view along the propagation direction of the light inside the substrate. Another problem is the total internal reflection. In order to be really substrate-guided element, the light should be reflected by total internal reflection from the external surface of the substrate. But usually we want to keep this element inside the glass, inside the lens, we want to protect it. So we want to isolate it from the external world. So we have 2 methods to do. One method is to use air gaps. This is what usually most of let's say, the company use today. Another method is to use isolation coating on the external surfaces of the substrate. This is very complicated and it's not practical. So let's say the only practical solution is to use the air gap, which also is quite problematic. Now, this is one of the most severe problems of a substrate-guided element. Most of the system, we want that the input aperture will be as small as possible because we want to have compact collimating system. On the other hand, we want that the output aperture will be as wide as possible in order to have a wide eye motion box and wide field of view. But as you can see, if we want to achieve these 2, which means to increase the output aperture that will be much larger than input aperture, the penalty is that we have to reduce the overall efficiency of the system. For instance, here you see we cannot use 100% here because we don't have enough energy for the rest of the elements. So for the LOE, the overall efficiency is bounded by 5, usually a few percent. For a diffractive element, the situation is much worse, is less than 1%. Usually it's few per mils. So you have to have very strong displacers in order, if you want to display your system for AR, for augmented reality, over the external scene. We cannot use, let's say, a system with low brightness as a OLED or micro LED. Okay, so I'm going to talk now about Oorym's technology. First of all, I want just to mention what is SPS. So the first time that, one of the first time that I demonstrate my technology, the guy who says, you know, it's a very smart idea. You should call your element a smart planaric subset. I thought, I cannot call my element a smart. It's like the, like the mankind call themselves Homo sapiens sapiens. It's ridiculous. You can call it, but I cannot call my element a smart one. But eventually we stick with the SPS. At the end of the talk, I told you what is the S. So you see that the SPS is constructed of just a simple paralleloid. The only difference between this paralleloid or the reflective element that I showed before, that here the angle is very, very steep. What is steep alpha surface can be 12, 7. We have even element with 5 degrees, which means now the tangents of this element, which is this angle is 85 degrees. We have that the external, the coupling out aperture could be very, very wide, even for a very thin glass. So you can see, assuming that this surface is parallel to this one and the major surfaces are also parallel to each other, we can have that the output direction is equal to the input direction. So far, it is very simple. But if go on, we can see that it is still simple. And now see what's happened if the rays encounter here at the right part of the substrate. Now we see that it's encounter double reflection, but don't be afraid. Now the second reflection is not our enemy, it's our ally. So we can see why, because here it's also reflected twice, it's a double reflection. So again, the input aperture is equal to the output aperture, and we can utilize the entire coupling out element. So this was our first pattern. By the way, we are so far more than 10 patterns, but this is the first one. And the main idea is that we, both the coupling in and the coupling out, use double reflection, even triple reflection, and even we have some system where we have 4 reflection from the input as well from the output surfaces. By the way, as you can see here, different rays from the same point, from that they have the same input direction, propagate inside the substrate by different direction. But eventually, after the coupling out, they retain the original direction. So we can have good image. Another problem that we have here, but we are going to solve, don't be afraid, is that the light are coupling out at an oblique angle. It's not normal to the major surface, but we want that will be coupled into the viewer eye. So what we use here a redirecting combiner that couple the light, that redirect the light into the viewer eye. It also serves as the, let's say the combiner. It's a beam splitter. So what we see here, that we have separation of variables. Instead of the other technology that use a single, very complicated element to couple the light out, so and also to serve as the beam splitter, here we separate the task. We have a very simple element that couple the light out, and very simple element that combine the light into the viewer. So simple plus simple still equal simple. The system is still simple. Eventually, as you see here, we put this coupling out element inside the prism in order to have a conform shape of the entire element. Okay, so another thing that we can make it even simpler, instead of using one thick element, we can use here an array of beam splitter. It looks complicated, but it's very simple because all the beam splitter, first of all, they are very simple. And second, they are identical to each other. So it's very simple procedure to prepare this, to fabricate this array. One more thing. You see, all the reflection here are from total internal reflection. Here it's total reflection, coupling by total and coupling out, and propagated inside by total internal reflection. And the only place that we lose the brightness is here by the redirecting beam splitter array. But eventually can achieve very high efficiency. The efficiency theoretically can be very close to 100% if the reflectance of this element is very high. But let's say for most of the system, the efficiency is between 20% and 80%, depends on the customer. And the net outcome is that we can use display source with low brightness. We can use OLED as a display source and make life very, very easier. You'll see in a minute. Okay, let's start now talking about the 6 axioms that we talked before. Large aperture, but we still have only a single coupling out element. So we still have a simple system, even so we can have very wide field of view. How much wide, you will see in a minute. But as you see, it is a single surface. It's uniform because it's a uniform coating. We don't have coating. We have just total internal reflection. We put the coating, we put in very simple AR to enable the light which reflectors we need to pass through it again without any reflectance. But it is a very, very simple coating. And the entire system is very simple. And we have wide field of view. This is a second axiom. Good image quality and low fabrication cost. We can also challenge this axiom. Why? Because this system is very simple. We can have good image quality. How good, you'll see at the end. But the fabrication stats are very, very, very simple. It's standard optical materials. It's very high index. It's close to 2, but it's commercially available by all the companies, Hoya and O'Hara and Short and Corning. I hope that didn't omit anybody. The coating are very simple, 4-level or 8-level. The cementing is conventional adhesives which are commercially available. The slicing is simple. Grinding and polishing of simple grinding and polishing machines. And last but not least, all the tolerances of our system are very relaxed. At the first step, we thought that we need very high parallelism between these two surfaces, two major surfaces in the order of few seconds, but now we relax it, let's say significantly, and the entire parameter, all the tolerances are very relaxed. I can tell you that we asked in the last few months whether we can go and manufacture our system with very high volume, which is why high volume, tens of thousands, 100,000. So we check with our suppliers and we get the answer that in 2 months we can erect a system that will supply this amount with reasonable price. Let's say it's completely different story from the other, let's say, system, other techniques that I know from my past. And the next time, let's now talk, next topic, let's now talk about plastic. So as I said before, because of the high efficiency of our system, we use only OLED or a micro OLED. So, you know, these display source do not depend in, they are non-polarized, they are not dependent on polarization. All the reflectances in the system is polarized and non-sensitive because it's total internal reflection. So we can use plastic. Another thing, all the tolerances are quite relaxed. So there is no problem to manufacture it by plastic. It's not accurate that it's no problem. There are some fabrication problem, but we hope that soon enough we'll be able to supply our market with plastic elements. Okay, now stay with me. This is a little bit more complicated, but it's still not very complicated. We can see that the upper limit of the external field of view is not bounded by the combination of the internal field of view and refractive index as the other technology. Why? Fortunately, we can use different refractive indices for the coupling out element, for the redirecting element, and for the main substrate. Usually, we use here very high index in the order of 2. The material of this redirecting element is BK7 or more float. The refracting is 1.5. So we get here quite a steep refraction. You see? Now, if you look on the equations of the field of view of the external field of view as the function of the internal field of view, we get very interesting result. You see that the field of view here in the redirecting element depends in the field of view in the main substrate. It depends, of course, in the ratio between the refractive indices, but also it depends on the cosine of these two angles, these two instances. Look again, now for the external field of view, when you get out, the field of view outside the substrate depend on the field of view in the redirecting element by the factor of the refractive index of the redirecting element. If you combine everything together, we can see that the output field of view is a function of the input field of view and the refractive index of the the main substrate, which is around 2. But also we have cosine term here. Here, the cosine is not our enemy, is our ally. To take an enemy and to make him a friend. So let's give an example. Let's say, again, let's say the substrate refractive index is 2. The refractive index of the redirected element is both floats, so it's 1.5 approximately. This is the angles, incident angles here in the interface plane between the substrate and the redirecting element. And let's assume also that the optics angle of this output surface is 7 degrees. If we make all the calculation, we see that the field of view inside the substrate is 13 degrees. Inside the redirecting element is 27 degrees, but outside it's 42 degrees. It's 42 along the propagation direction, which means that we can get in eyeglass configuration a field of view of more than 50 degrees. So you can ask why to keep this internal field of view so small. We can increase it a little bit, but you see it next transparency. Okay, now we talk about how we can encapsulate it without isolation layers. So as you can see here, we have two interface plane. We have interface plane between the substrate and the redirecting element, and we have an interface plane between the substrate and, let's say, the completing prism. So if, again, we take the same example, but now, as you can see, the minimal angle inside the substrate is 51 degrees. This is why we kept the internal field of view quite small to have minimal angle, which will be quite high. And since the refractive index is very high, it's 2, what we got that let's say the refractive indices of these two interfaces is this value 1.34 and 1.38. These refractive indices can easily be achieved by using commercially available adhesive. So we can achieve isolation without any let's say, complicated coating and without having to resort to air gaps. Okay, now this is the major difference between our technology and the other. And this how we can laterally expand the coupling out and still have very high brightness. So if you see about this system, say, okay, it's also very interesting story, but we see that here, not only the output aperture is very large, but the input aperture is very large, which means that you have to use enormous collimator. You have, let's say, very monstrous system if you really want to have a good system. Not true. So stay with me and let's see what's happened. So fortunately, you see that if you're going from the eye into the substrate, you see that each illuminating wave illuminates only part of the coupling out element. It's correct for the other technology, but for our technology, it's quite advantageous. So let's start with the left marginal ray. We can see that it illuminates only the left part of the coupling out element. It is reflected 3 times from the input as well as from the output. Okay, this is nice, but the outcome is that the light, which is coupling out from the left of the output, is coupling in from the right. You see? In a minute, see why it is important. The central ray is coupled after to reflection and coupling in also after to reflection, which means that it coupled out and in at the central part of the coupling in and the coupling out element. Now, let's see what happened to the left marginal ray. We can see that it coupled at the left, at the right here, and coupling in at the left, just the opposite of the left marginal ray. So let's combine all of them together. What do we see? We see this, let's say, quite peculiar behavior of the output image. But you see, seemingly, we've not achieved everything, but still the coupling in aperture is equal to the coupling out aperture. But look on this direction. Just pay attention. Let's say that for a regular system, for conventional system, if we get out of the eye and trace the rays backward, we see that the light rays are converged from, let's say, for the system. So we have to put the collimating lens here, which, well, in a lot of time, it should be a very large collimating lens. In our case, it's just the vice versa. Because of the right go to left and left go to right, we get this behavior. We get that the light rays, the input ray, or let's say the output ray, if we go from the eye backward, we see that the output light rays, instead of being convergent, they are instead of being divergent, they are convergent. And now let's see what we can do. Instead of coupling the light here, when they illuminate quite a large aperture, we let them to continue stay in the substrate. We put a folding prism, and here we have a point when all the rays are contracted into a very narrow aperture, which means that the input aperture is much smaller than the output aperture. How much smaller? We have some example when here it's 6 millimeter and here it's 24 millimeter. We can expand it by a factor of 3 or 4 without losing even 1% of efficiency. Okay, so just as another thing, it's not connected to the other axioms, that there are some systems, especially the diffractive, that when you look from outside on the user, you see what he sees also. It's also diffracted back into the external scene. It's not exist here because all the light which are not coupled to the light are just disappear here. If we put a proper AR, the external viewer will not see anything from your eyeglass. So before I finish, I just want to quote the wise of the wisest, Miguel de Cervantes, who wrote in Don Quixote that the proof of the pudding is in the eating. So far, I told you a lot of stories. But we know that when we test a visual system, an imaging system, the one thing that's important is the image quality, is the taste of the pudding. So unfortunately, we know that last year, most of us lived in a quarantine and had to spend this time by cooking and baking a lot of good stuff. So I want to say that here in Oorym, we use this time to prepare an excellent pudding, and you are welcome to taste it. So I hope that in a short while, this quarantine, this, let's say, pandemic will go over and we can visit ourselves, and I will be able to show you. In the meantime, just to show you briefly a few photographs that I took from our system. This is an image that I took from my windows in my room. It was in the high noon time, and you see that over the blue skies, you can see very sharp and high contrast image. The source is OLED, no image processing, no filter. This is the image, let's say the bare image. This is a second example. I took it inside my room. You see that this is the image that we get from the computer. You just inject it, and this is the image which is floating in the air. You see that it's bigger, much brighter, and no deterioration in the quality of the image compared to the, let's say, the original image, which is image through the entire system. Before I finish, I promise you a story. So this is the story about, maybe it's not a story, maybe it's not an urban legend, but it's a very good story, so I'll tell it anyhow. It's about the American space program. When they initiate the program, they encountered with quite a severe problem. When they tried to write in the let's say, the outer space, it's that in zero gravity, you cannot use a pen. The droplet of ink started to float in the air. So they have to invest a lot of money in order to develop a very, very complicated pen that can write in zero gravity. So the time has passed, a decade passed, and as a result of the detente, the Russian and the American launched, let's say, a common, a joint venture program. You see, this is the Russian Soyuz, this is the American Apollo, and they start to work together, to cooperate together. So when they get ready to, when they have some discussion before the common mission, the American asked the Russian how they tackle with the problem of the pen, of the ink, the zero gravity. And the Russians said, of course, we know about this problem. The Americans said, how did you solve it? And the Russian answered, we use the pencil. So you see, sometimes the best solution is the simple one. And SPS is a simple planaric substrate. Simple. Thank you very much.
Thank you very much, Dr. Amitai. A great pudding. And, you have a question on the Q&A and also in the chat.
Okay.
So please, can you see these questions?
Okay, just a minute. Okay, I'll stop the sharing. Okay, I'm ready for the questions.
The questions are in the chat. Can you see the question?
Can.
Okay.
Can Oorym's display show black content? Okay, I don't know what is black. You cannot. There are no black photons. Black, which means that you don't that you don't project any photon. This is black. If the, let's say, if the external scene is black, then you see black. But if the external scene is bright, you cannot turn it off by your own system. So you can use our, let's say, our system is very high contrast, but you cannot project black photons. But as I said before, if you have very bright image, and you can have bright image with our system, you can have high contrast and good image. But if the, let's say, if the external scene, the background is bright, it will stay bright. I hope that I answered this question. If you want, please ask again. So the second,
you have more questions in the Q&A and also in the chat. So don't miss.
Okay,
don't
now
miss both.
First of all, I answered the question in the Q&A. Another question is, what is the maximum field view you can get? Let's say the maximum field view that we got so far is 42 degrees in the propagation direction, which is around the 50-something degrees diagonal. This is for, let's say, a side illumination. For top illumination, since the aspect ratio of the image is completely different, we can get a much wider field of view. What is much 60, 70 degrees? We didn't, let's say, we don't know for sure our limits, but it could be much wider than we got so far. Why can't holographic diffraction grating works? Well, it works. There are a lot of systems that work with a diffractive element, but as I said before, there are some problems. I believe that there are some diffractive systems that got good imaging after, let's say, putting a lot of effort in it, but how much is it good? I don't know. I cannot judge it. Okay. What is the thickness of the SPS? Very good question. It depends on the field of view, it depends on the requirement of the customers. So far, we have a system, let's say the system that I showed you before, which has a field of view of 50 degrees. The thickness of the main substrate is 2.5 millimeter. We have some method how to decrease the thickness to around 2 millimeters. Let's say for a lower field of view, it could be much thinner. So far, we have a system for, I can show it to you. You see this one, the thickness is 1.5 millimeter, and we can have some similar that will be 0.9 millimeter, the main substrate. By the way, I can show you, this is the entire optical system. This is 25 degrees, this small field of view. You see, this is the entire, this is the substrate, and this is the collimating element. You see, this is 0.6 on 0.10. This is the coupling out, let's say the output aperture, and this is the, let's say, this is the display source. This is the entire system. The entire weight is 12 grams. And it is very, very simple. Okay, is there a waveguide length limit to keeping good image quality? Well, I believe that the problems will be when we start to, when we have to, let's say, when the absorption become too high. So far, let's say for the near eye display, it's good enough, all the material that we know. For, let's say, for head-up display, usually you need much longer, but also for head-up display, we have solution. How much long, I don't know, but I think a few centimeters and a few tenths of centimeter, we can have a solution. So there is no strict limit for it. What is see-through efficiency? How much it's deformed? The see-through efficiency depends on the reflection efficiency. You can, let's say, put it 50-50, which means that the see-through efficiency will be 50 and the reflectancy will be 50. You can choose any other desired ratio according to your requirement. We have also some solution where we can use dynamic element we have not built yet, and then you even dynamically can choose whether to project more or whether to let the light, let the external be transmitted more. What is the transparency of the turned-off system? This is, as I said before, it's dependent on the reflectance of the beam splitter. If the transmittance efficiency is 80%, then let's say the contrast is very, very high. Our boss displays technology equally effective when utilized with no, I believe that micro LED or LED or anything that has, let's say, we can use any display. We can use also LCOS or laser, anything that you want to. We just found the OLED the more convenient and with higher contrast. But let's say if tomorrow ask us with something with very, very high brightness for a few thousand foot Lambert, of course, we have to use LCOS. We cannot use OLED. So we can use any, let's say, any practical displays of our how high is the see-through transparency of the output converter? I answered this question before. It depends on the system. It could be any value that you like to. So, okay, I open now the chat. There is no. Okay, let me start from the beginning. Okay. Okay, just a minute. Arbos, if data technology, how can I increase this chat? Can I increase the chat because it's very limited?
I propose that this question will be sent to you directly to your mail, and then you can
Okay, I can read it.
answer.
I can read it. Just a minute.
Because we have only 5 minutes more, and then we have to leave
Okay. I open it. Just a minute. Are both display technology equally effective when utilized with Oorym? Okay, I answered this already. Okay, thank you very much. What is the system for efficiency? I also answer. Okay, another question. When it will arrive to the market? I hope that very soon. We have so far we have some client that ask for, let's say, specific system. When we start preparing them, it's not dependent on us. It depends when a customer will ask for a system, but we are ready even a few months to deliver this system to the market. For let's say, very compact system, having moderate field of view of something like 30 degrees, or for more complicated, not more complicated, we are only simple, for a different simple system that have very field of view of larger than 50 degrees. Can we get the video of the presentation? Shlomo, you should answer this question.
The answer is yes.
Okay, very good. Other questions? Just a minute, I see another question. How can we get it? How can I get a system? When we start delivering it, I promise you that we tell everybody how can but you can offer, of course, you can keep the contact with me, but I hope that will be very, very soon.
I'm sorry that we have to finish, but if somebody have any further questions, you are most welcome to email me, Nofar, at aei.org.il, and I'd be happy to assist and transfer the question to Dr. Amitai. Thank you all for coming.
By the way, you can find my details in the LinkedIn, and anybody who know me directly you can email me also directly, the one who had my email.
All right, Dr. Amitai, thank you very much. It was a great lecture, and we hope to see you again in our club.
Okay, thank you very much.
Thank you. And